Hey everyone, welcome to our poster on unsupervised multilingual alignment using Wasserstein Barycenter. This is Joy, work with Shin, Jacob, Pascal, and Yaolian. And in this work, we're interested in learning the unsupervised translation. So by that, I mean that like we're given M languages, each with its own vocabulary and word embeddings. And we want to learn the mapping between each pair of languages. Just note here that we don't have any parallel corpora here. So this problem has been widely studied in NLP. So if you have the assignment matrix P and the projection matrix Q, if you know the assignment matrix in advance, then basically you're trying to optimize over the Q in a supervised setting. If you want to, in an unsupervised setting, you're trying to do a joint optimization over on both Q and P. So also like this problem had some nice connections with optimal transport theory. So there's been like a lot of recent work in that area. So our work is mostly inspired by the work of Jean Alex et al. From the Isla 29 paper. And the way they formulated is like they formulated a joint alignment approach that minimizes the cost of misalignment. And one thing that you note here is that like once you try to put like transitivity in the permutation of the assignment matrix, then basically this boiled down to like a closed form solution given in equation 6, which is basically saying we're trying to take an arithmetic mean of all the languages, or in some sense, some mean of the languages. And what we argue here is that like instead of taking an arithmetic mean, or even like for instance like some fixed pivotal language, we argue that we take Wasserstein Barycenter as the pivot of all the languages. And why is that better? So that should be slightly evident from the figure 2, where we're given a couple of two distributions, and then as compared to the L2 mean, the Wasserstein Barycenter is much smoother and sort of like unimodal. And so the approach, basically, to summarize the approach, is that we take all the languages, compute the Wasserstein Barycenter, and learn the mapping between the coupling between the language I and the Wasserstein Barycenter. And once we have learned such a mapping, now to infer pairs between like the language I and language J, we can just multiply their couplings. So how do we compute couplings? So details are in paper. And by using this, basically what we show is that we sort of get like state-of-the-art results on a few data sets. And here I'm showing the data on Muse, the very widely known data set. So all the results are in question 1. And then if you can see that like our algorithm outperforms most of the current best methods on most of the language pairs. And even on average, it outperforms about 1.5 to 2% better. And what we have shown in sort of table 2 is that like our work can also be useful for the polysemous words. So the words, I think that would be a good contribution in the sense for the community. And the extended version of this paper will appear in ICHKAI. So I hope you guys read the paper. And yeah, thanks a lot for attending the presentation. And please feel free to ask any questions. Thank you so much.